The Tower of Hanoi is one of the most famous recursive mathematical puzzles and a classic problem in the study of algorithms and data structures, often used to illustrate the elegance and power of recursion. Invented by French mathematician Édouard Lucas in 1883, the puzzle consists of 3 pegs, traditionally labeled A, B, and C, and a number of disks of different sizes arranged in decreasing order on one of the pegs, with the largest disk at the bottom and the smallest at the top. The objective is to move the entire stack of disks from the source peg to a target peg. Following 2 fundamental rules, only one disk can be moved at a time, and no larger disk may be placed on top of a smaller disk. Although the rules appear simple, the problem's complexity grows exponentially with the number of disks, making it a powerful example of recursive thinking and algorithmic design. The recursive nature of the problem becomes evident when we consider how to move n disks. To move the nth, largest, disk to the target peg, one must first move the top n-1 disks to the auxiliary peg, then move the nth disk to the target peg, and finally move the n-1 disks from the auxiliary peg to the target peg. This naturally leads to the recurrence relation T, n, equals 2t, n-1, plus 1, where t, n, represents the minimum number of moves required to solve the puzzle with n disks. Solving this recurrence yields T, n, equals 2 n-1, demonstrating that the problem's complexity grows exponentially, and illustrating why even a modest increase in the number of disks makes the puzzle significantly more difficult. For example, solving the puzzle with 3 disks needs 7 moves, 4 disks needs 15 moves, and 10 disks needs 1023 moves. This exponential growth makes the Tower of Hanoi a useful benchmark for studying algorithmic performance and recursion depth. On a conceptual level, the puzzle teaches how complex problems can be broken into smaller subproblems that share the same structure, which is a key principle of recursive algorithms. Implementations of the Tower of Hanoi in programming commonly involve a function that takes the number of disks and names of the source, auxiliary, and target pegs, and prints or performs the necessary moves, demonstrating how recursion models the problem with clarity and minimal code. Beyond its educational value in computer science, the Tower of Hanoi also has deep mathematical significance. It is closely connected to power of 2 sequences, binary number systems, and fractal patterns. The movement of disks can be mapped to binary counting, where each disk represents a bit flipping between states. The structure of the solution also forms a Sierpinski triangle when visualized, revealing a fractal nature inherent in the recursive sequence of moves. The puzzle even appears in theoretical discussions of the limits of computation and time. A popular legend associated with the puzzle describes monks in a temple moving 64 golden disks, according to the Tower of Hanoi rules, with the prophecy that the world will end once the puzzle is completed. Given that solving the puzzle for 64 disks requires 2 to the power of 64 minus 1 moves, which is over 18 quintillion moves, and assuming 1 move per second, the process would take over 500 billion years, far longer than the current age of the universe, highlighting the immense scale of exponential growth. From the perspective of algorithm design, the Tower of Hanoi exemplifies the principles of divide and conquer. The problem is solved by dividing it into 2 smaller subproblems of size n-1 and a single move of the largest disk. The elegance of the recursive approach lies in its symmetry. Both subproblems follow the exact same rules and structure as the original problem. This makes the Tower of Hanoi not only a puzzle but also a model for understanding recursive data structures like trees. Each recursive call can be visualized as a node in a binary tree. where the left branch represents moving n-1 disks to the auxiliary peg, and the right branch represents moving n-1 disks to the target peg, forming a complete binary tree of depth n. This conceptual link deepens students' understanding of recursion stack frames, function calls, and the idea of backtracking. In practical applications, although the Tower of Hanoi itself is not used directly in real-world systems, its principles are embedded in various computational techniques. For example, recursive problem solving, stack processing, and divide and conquer strategies are essential in algorithms such as merge-sort, quicksort, binary search, and tree traversal. The puzzle also finds applications in cognitive science, where it is used to study problem-solving behavior, planning skills, and memory functions in humans and artificial intelligence systems. Psychologists use Tower of Hanoi tasks to analyze executive function, particularly in individuals with neurological disorders, because the puzzle requires careful planning, working memory, and the ability to foresee consequences of actions. Similarly, robotic researchers use the puzzle to test planning algorithms and autonomous decision-making in robots, where the robot must plan multi-step actions to reach a goal. In computer science education, Tower of Hanoi serves as a foundational example that bridges theoretical and practical learning. Students learn not only the recursive algorithm but also how to convert it into an iterative approach using stacks, illustrating the equivalence between recursion and stack-based iteration. The puzzle also helps explain Stack Overflow errors, as large n values require deep recursion that exceeds memory limits. Overall, the Tower of Hanoi stands as an enduring example of mathematical beauty and algorithmic design. It captures the essence of recursion, demonstrates exponential growth, connects deeply to mathematical structures, and serves as a practical teaching tool across disciplines. Its simplicity of rules combined with the complexity of its solution continues to fascinate learners, researchers, and scientists, making it a timeless subject in computing and mathematics.